So hello everyone. So I see not only a lot of students, but also quite a few old friends. So here I will say hi to every of you, and also I'm feel really honored by invited by Professor Shi that give me this opportunity to share what is happening in this area, specifically the how can we apply the machine learning techniques in the smart transportation. And our lectures in total, we will be having two. So one is the high dimensional data, specifically tensor in the smart transportation. And the second half, which is in 2 days, we will introduce deep learning in smart transportation. So before I officially get started, so I will also introduce myself a little bit, either both formally and informally. So this is the research I'm focusing on, is the spatial temporal analysis. So basically we apply it a lot in the smart transportation. And I have been long-termly doing research in tensor or smart transportation and also anomaly detection. And recently I also started to explore new areas such as self-supervised learning, reinforcement learning, and causal structure learning. So apart from research, so usually you can also find me quite often in the hiking trails. So I like hiking a lot. And also another two things I want to use to define myself is that, okay, I get my PhD in this wonderful city. And now I'm also working in another beautiful city. So overall, so I hope this is an image about myself. So as you already discovered either in the syllabus or in the introduction, that today the data we are going to talk about is called spatial temporal high dimensional data. So what is exactly the spatial temporal high dimensional data? So we start from small. So if we only look at the temporal data, we are quite familiar with that. For example, it's basically time series data that the value is changing over time. But if I tell you now that, okay, this time series now is taken from this location, the blue location, and if we switch to the green location, then the time series will behave differently. So then we can say that the spatial information also play a role about how the data are gonna behave. And so far, we call it the spatial time series. And so far, the spatial dimension is still the fixed location. And things can be more complicated. For example, the location can be dynamically changing. So in that case, we can call it a trajectory. So these two types of data is basically quite popular in the smart transportation. And usually the data comes as a high dimensional, which means a lot of dimensions or features involved. It sounds really scary, this kind of data, but do we have a lot of examples? Yes, indeed. So for example, in the stock price data is a typical spatial temporal high dimensional data. For example, green maybe is the European market, red is Asian market, or blue is US market. So you can say, okay, different market inside of this, inside of each market, they may show some similarity, and over the time it's also changing. So it's a typical spatial temporal data. And also back to the transportation area. So in this map, we can see that, okay, different locations, the traffic volume, some is higher, so it's more red, some is lower, so it's more blank. So, and the heat map is also changing over time dynamically. Another type is traffic dynamics trajectories. This is dynamic. We can see that it's moving, right? So these are really typical spatial temporal high dimensional data we can see. And the core for the most of the spatial temporal data analysis is trying to capture the spatial temporal correlation. And this is really important. I will highlight here. So before we start to model, okay, how to capture. So we explain the concept a little bit more, that, okay, this kind of data not only in the transportation is popular, but also in a more broad sense, that more than 74% of the data in the internet we see is spatial temporal high dimensional data. For example, in the manufacturing, the signals from the multi-channels, or even the text changing over time, Twitter posted over time and the different countries, and also this kind of bird monitoring videos. So once again, the challenge is the complex spatial temporal correlation. And back to the smart transportation area, usually we say, okay, there are three basic domains or the categories inside of the smart transportation. So one is what we call the traffic static data, which is referring back to the spatial time series we talked about. For example, the flow, the speed, and also the saturation rate of the each road segments. And the corresponding task can be quite diverse. We can do prediction, imputation, correction. I will talk about it in second lecture, anomaly detection, and maybe more general, just representation learning. And the method can be the traditional ones, such as statistical learning, tensor method, and also maybe more fancy one, self-supervised learning. And the second type is the traffic dynamic data. So it can be the trajectory indoors, can be the trajectory outdoors. Indoors, for example, inside of a museum or inside of a shopping mall, how do you use the indoor trajectory to better navigate? And also, you say my mouse is moving, so the trajectory of the mouse can be also considered as a data we can analyze. So this can be used for some, for example, fraud detection or some other applications. And the task usually can be trajectory recovery or also generally representation learning. And usually the method can be sequence to sequence method. And the third type is trajectory overall management. And the task is that we combine the heterogeneous data from either the static data or the dynamic data, or the data we can get to optimize, for example, the traffic signal control, or to better manage the traffic congestion situation. So the method we can use sometimes is reinforcement learning, sometimes it's the Bayesian network. So overall, this is the overview about how machine learning techniques can be applied in different domains inside of the smart transportation. And for us, for today's lecture, we will focus on the prediction task. And we will use the method, specifically the statistical learning and the tensor method. So why prediction? So this is the map of Hong Kong metro stations, and you can see in such a crowded city, it can be really crowded during the peak time. So if we want to do the prediction, we need to understand the data better, the data set. So in Hong Kong, usually there are 5 million passengers traveling inside of the metro systems every day. And back in 2017, there are almost 100 stations, 11 lines, and the metro runs almost through the whole year, 21 hours per day. And why prediction is important? Because we can understand the question in two ways. For example, for the long-term prediction, for example, several days ahead, this long-term prediction can help the metro companies to better arrange the operations and the management and the scheduling things in advance. And the second concept is the short-term prediction, for example, a few hours ahead, that this is more like a, if overcrowding is happening, then they can respond in a really timely way. And it's also important, since we have 100 stations, it's also important to offer the prediction for the 100 stations simultaneously, instead of, okay, predict one station after one station, then that's not efficient. And even for this task, just focusing on the prediction in such a tiny city for 100 stations, even this task can be complicated. And why? Because we talk this concept a lot, and because of the complicated spatial temporal correlations among the regions. So now we need to understand what kind of spatial temporal correlations we are talking about from this specifically this metro data set. So some fun thing about the metro, you can say across different countries, they have different names. Some is kind of different and similar at the same time. So in Hong Kong, you call the MTR. In New York, you call the MTA. In Singapore, you call the MRT. Yeah, UK and Germany always being different, underground or U-Bahn in Germany. Yeah, so so we are trying to analyze the passenger flow on each station, and this is the original data, how it looks like. So it's the anomalous passenger ID coming, entering this origin station, for example, station 1 at this time, T1, and exit at these different destinations at different time. So far, let's just focus on the entering. So we ignore this part first. And if we only focus on the inflow value of station 1 at T1, we can say, okay, now it's 3, right? And so far, just at this time point, if we look at through 24 hours, then we can get a nice plot about this station 1, right? And if we look at more days, for example, 10 days, then we can say, okay, maybe some patterns, but it's not that clear enough. So if we put the 10 days in a row, then we can see really nice patterns now. So temporarily, we can say that, okay, it's every week from Monday to Sunday is a cycle. So 7 days as a cycle. And also during the week, we have pattern 1, and on the weekends, we have another pattern. It kind of makes sense, quite intuitive, right? So this is the temporal pattern, quite intuitive. And the spatial pattern can be quite complicated. So you see, I randomly picked 36 stations here. We can say that, okay, some stations, it has a morning peak. Some stations has the afternoon peak, evening peak around 6 p.m. And some stations have dual peak, double peak in the morning and in the afternoon. So why is that? So I will keep this as a question and I will answer it later. So overall, we can see that the spatial patterns are quite complicated. And our goal is to predict all the stations simultaneously and hopefully very accurate and very efficient. So what work has been done for the spatial temporal prediction? There are several works. If you search in the Google Scholar spatial temporal prediction, you can find around 300,000 papers about that. And 1/3 of them is use deep learning techniques. Another 1/3 is use the traditional time series method, for example, ARIMA or hot winters. And if we look at the time series data and the time series model or the neural network models, of course, neural network models can be very strong, but it's quite computationally costly to train, and maybe it's not that easy to deploy it in the front line if there's no GPU or a strong machine. So maybe it's not that practical to deploy it. And the time series model, it has the big disadvantage that if we have 100 stations, then we need to train 100 different time series separately. That can be also not efficient. So we have the concept tensor that comes in, that the tensor is known for that it can preserve the innate complex and spatial temporal correlations. So what is exactly the tensor means? So by the way, the method that uses tensor to do this question is quite how to say, is quite unique method. So it's kind of in the top of the pyramid. So what exactly a tensor means? So a tensor is called a D-way array, and you have all seen the tensor before. So if D equals to 1 is a vector, if D equals 2 is a matrix, D equals to 3 is a cubic, and if D larger than 3, then can be quite complex. So I found a beautiful picture for it. So that's our metro station. The passenger inflow data look like a tensor. Can be formulated as a tensor? The answer is yes. So how? So for example, this is the passenger inflow for station 1 and day 1. We can basically write it as a vector, right? Across this time dimension. And it's only for 1 day. If we look at, for example, 50 days or 60 days, 2 months, then we can get a matrix for station 1. And now it's only station 1. If we look at station 2 and all the way to station 100, then in that case, we can formulate our data in a 3-order tensor with the dimension of station at different day, at different time, was the passenger inflow. So each value inside of the 3-dimensional tensor is the passenger inflow. So to understand the tensor decomposition, and this is a really basic technique for our method. So before we understand the tensor decomposition, there are one important basic concept is that called rank 1 tensor. This is basically the building block of the tensor decomposition. So let's start from the matrix way. That, for example, we have 2 vectors with the dimension m times m and n. So the outer product of A and B is basically a matrix with the dimension m times n. So basically, the matrix here, this element is the we get by multiplying the ith from A and the jth from B, right? So in the tensor version, then we basically have 3 vectors with dimension m, n, and p. And the value here in the ijk inside of this tensor is basically the ith from A, jth from B, and the kth from C, right? So it looks like a chicken foot. So in this way. So here we call it is a rank 1 tensor. And here we can call it this is a rank 1 matrix. But in reality, our matrix or our tensor can have multiple rank. So the real tensor or real matrix can be the summation of different of R matrix sum up together. And similarly, our tensor can be the R rank 1 tensor sum up together. So mathematically, it can be written like this. So the only difference is that, okay, we sum up R different rank 1 tensors here, the big R. And we can write it in a more simple way that we combine all those A together, then we say it's matrix A, all those B vectors here, then it's matrix B. So similarly, we get ABC. And for example, if we normalize ABC, then we add a weight vector lambda to scale back to the original scale. And the way how to learn A and B is the way that, okay, we want to minimize the difference between the real X and what we reconstruct by the outer product, M. So this is called rank one. This is called tensor decomposition, and specifically for this type is called CP decomposition, that we decompose a tensor into a weight matrix, and along each dimension, the mode, a weight vector, and along each dimension, we have the mode matrix ABC. And this R is called the rank for CP decomposition. And for the target decomposition, then I will make it faster. The target decomposition is basically also the higher dimensional version of the SVD, the singular value decomposition, that we decompose matrix X into A and B, and also the sigma here. Sigma is more like a covariance matrix, something like that. And similarly, for the target decomposition is a high order version of SVD that we decompose the tensor IJK dimension into a core tensor with the dimension of P times Q times R. And along each dimension, we get the mode matrix ABC. And here, you can see that the PQR is what we call the rank for target decomposition. So here I have a small quiz for all of you that you can click inside of the. I can also send in the chat box. That yeah. So the question is. So we introduced two decompositions now. So which one do you think generally is stronger or more complex? So whether it's CP decomposition or target decomposition. So I will vote for target decomposition because I know, yeah, most of you also get it. Why? Because, okay, let's switch back. Because we have more rank here, the PQR. This is the rank for target decomposition, which means it has actually way more parameters to be learned than the CP decomposition, which means the model target decomposition generally is more complicated than CP decomposition. So that, okay, if we have really complex data, so maybe it's better to use target decomposition to capture the complex data behavior. So this is target decomposition. So I will introduce two methods now. How can we use the tensor and the tensor decomposition for prediction? So I will start from the long-term prediction first, and then the short-term prediction on the second. So for the long-term prediction, we use a two-step tensor decomposition, which means the first step, we decompose the tensor, and the second step, we use the typical time series model. So how do we do that? So imagine this is our tensor with the dimensions station, time, and day. We want to do long-term prediction, which means what's the passenger value in next 2 or 3 days. So it's along this dimension, along this day dimension to do prediction. So our first step, for example, we use CP decomposition. We can also use target decomposition, and they are all good. To get the mode matrix along each dimension, we call it U day, U time, and U location. And for this U day, we will use the second step, the general time series model. And here we specifically use 2D ARIMA model. I will explain why. So basically we extend or predict this original U day for the next tau days, which means we make this matrix a little bit longer. And once we get this extended matrix on the day dimension, we time them up with the original U time and U location back to get a new tensor. And this new tensor, we have along the time dimension, along the day dimension, sorry, we have additional tau steps. So this red part is basically the prediction. And by this one click, then we can get the prediction for all the stations at the same time. So this is quite tricky, quite small design, but it works really well. So this is what we call two-step. And now we will focus on why here we use 2D ARMA model. So the intuition is like this. So for example, this was the data from the 2017, so it's quite old, 5 years already. For example, we want to predict the Thursday on this day. So this Thursday's passenger flow should be similar to 1 day before Wednesday and 2 days before on Tuesday on the same week, right? So it's basically the same week W, but D-1 and D-2. And also, it should also be similar to the passenger on the same on Thursday, but 1 week ahead, 1 week before, and also the Thursday 2 weeks before. So it's the same day, but W-1 and W-2. So this is the idea of the 2D ARMA model. So that, okay, for this U day, this matrix, for each column is each rank. So for each rank column, we rearrange it as this Monday to Sunday times different week. So that when we are predicting this specifically this value, we use 2 lag back on the week dimension and also 2 lag back on the day dimension, so that we can capture all the important informations. So this is the purpose of the 2D ARMA model. And here is more like we get an intuition from the temporal correlation. And why it works? Because the mode matrix we get actually has quite a lot of meanings. For example, this is the day mode matrix. You can see that, okay, the Monday, Tuesday, all the way to Sunday, the pattern can be also represented in the mode matrix. And similarly, this is also the real prediction result by the 1D ARMA model. So you can see that, okay, this is the prediction result, and this is for the U-day matrix, and this is the real prediction, and you can see it's quite accurate, except on Saturday. Why? Because it didn't capture the weekdays correlation. So that's why the 1D is not good. So here is the result for the 2D ARMA model. As you can see, the 2D ARMA model can have almost like 20% improvement than the 1D ARMA model plus the tensor. So this is the trick, yeah. And this is how the new prediction look like. So I didn't show the day, but this is Saturday, and you can see the prediction is also quite accurate. Yeah. So this is the what we mean by the meaningful information from the mode matrix. And similarly, in the station mode, we can have the same, also the really good information inside. For example, we do the PCA analysis to decompose this station mode matrix. And for example, we choose the top 6 pieces, and then we to represent it. And then we use the typical hierarchical clustering method to cluster different stations by just use the use station, this matrix. And we can get some really interesting station clusters. For example, here, station 39 and 80, you can see that the two code 39 and 80 is quite far, which means the two stations are geographically quite far. But you can see that they all have the green land use color, which means they have the similar functions. And that's what we call the contextual information. And also you can see this 71 and station 69, they are quite close to each other, just two stations away. So now in this case, even though their land use are quite different, but they are still in the same cluster. So you can see that, okay, even we didn't specifically formulate the spatial correlation, but the information is still well preserved. So this is the power of the tensor mode, tensor data formulation. And so now, what if I tell you that, okay, our data, there are some part is missing. No matter whether it's matrix or it's the tensor. So in this case, can we still use our method that, okay, we still use to learn this, this decomposition, and can we get good decomposition result? And can we use this decomposition result to infer what's the missing value? Yes, the answer is yes, we can do that. And this technique called Tensor Completion. So basically it's the same thing that, for example, in the matrix wise, we want the matrix M is decomposed by A and B, is on the observation side, on the observation set omega, M should be equal to X, right? And when we decompose, the M should be as close as our reconstruction result A and B. So we have the two terms here, and similarly for the tensor completion is the same. So here I will introduce a little bit more in detail later. So, but the thing is how the tensor completion can be related with prediction. And that's exactly the second prediction, the short-term prediction we will talk about. So how can we use the tensor completion for the prediction, and especially for 2 hours ahead prediction? So here, for example, this is our new tensor. We already observed in the new day that, okay, until 11 a.m., we don't observe anymore. We are right now at 11 a.m. How can we predict the rest of the day or for 2 hours? So we use tensor completion in a way that, okay, we assume the historical data is what we observe data, and the prediction horizon is the missing data. So this is how we formulate it as the tensor completion method. So this is our input X, and we want our output Y. So in the observation set omega, the green of the Y should be equal to the green of X, right? And also our Y needs to be complete for the red part. And we also want our Y has this, so this is the observation indicator, is another tensor. And we also want our Y has this nice decomposition we formulate. For example, we can use CP decomposition. So this is how we formulate the short-term prediction as the tensor completion way. So for the matrix, for the ABC, we can write it in a more general way that we don't only consider 3 dimensions. We can consider, for example, k dimensions. So we can write it in a more general way, like U1 all the way to UK. And usually we normalize all the vectors so that we also need to add another weight vector here to rescale the reconstruction back to the original scale. So this is the overall formulation, and this is called the tensor completion for prediction task, and we were the first to propose this model. So back to Google Scholar again, that okay, they are really rare attempt to use the tensor completion for prediction, and we prove that it works really well. So we will show how. So we did our first try. That okay, this is our input, and this is the CP decomposition structure we wanna the Y has, and also we don't wanna the lambda to be too big, which means we don't wanna our rank is too high. Otherwise, it's gonna be too complicated. So usually we can add L1 penalty on the lambda to achieve the low rank. So this is called low rank tensor completion. And our first try was actually not that good in some specific stations. So for example, the black one is the ground truth, the average of the ground truth, and the red one is the some locations has some stations has really good prediction. So it's quite close to the ground truth. But you can see that some blue stations, they are quite bad predict. So why? So we checked in the map that, okay, those good predictions, they are kind of concentrated inside of the, in the center of the network. And those badly predict stations, they are located in the kind of the outskirts of the network. So this is the first reason we found that location, okay, maybe play a role. And also we collect what's the surrounding facilities of these 5 stations. And you can see that they all have a really dominating land use pattern, not like the other 10 stations, which is more like uniformly distributed. So maybe this is also another reason. So if we formulate it officially, so this is the reason one, that the spatial correlation now plays a big role. That, for example, we get the correlation map of different stations, and we can see that, okay, in this block, station 50 and 60, they are quite highly correlated because they are geographically close, because 50 and 60 is quite close. And we can also see that in the map, that if we randomly pick 2 really close stations, for example, this one, they all have the evening peak. And if we choose these 2, they all have the morning peak. So the geographically being geographically close kind of explain why they have the similar passenger flow pattern. But what's the deal with this block? That you can see the station 50s and the 80s, they are quite close, they are quite highly correlated. Why? So this we call it is maybe because the contextual similarity. And we can also find it in the map that, for example, this station 50 are quite far away from the station 70s, but they are all located in the residential area, so that they all have the morning peak pattern. So now explains why some stations has the morning peak inflow, because in the morning around 7 or 8 a.m., people need to go inside of the metro station, take the metro to go to work, right? So this is why there's morning peak. And this station 10 is far away from these stations, but they are all located in the office area. That's why it has the evening peak, because around 8 p.m. or 7 p.m., people leave the work. So that's why it's the morning peak, it's the evening peak. So then we can observe 2 correlations that the geographically close make the 2 stations have the similar pattern. And also if they are located in the similar functional area, so in that case, if they are far away from each other, even though, but they still have the similar pattern. So we call it the geographical graph and the functional similarity graph. So these two graphs play a role. But that's not the only reason. So another deeper reason is that, okay, it's exactly because we have this graph on the station dimension. Now our data is weakly dependent. So what do I mean by weakly dependent? It means that if any two stations are randomly picked, then they are really less likely to be highly dependent if they are not connected in either of the graphs. So for example, in the big graph, we randomly pick two, they are really less likely to be the neighbors, so that their passenger inflow pattern can be quite different, like this case we demonstrate. And if we look the whole map, so actually indeed their correlation is quite kind of blue, which means weakly correlated. And so we call this station dimension as the weakly dependent dimension. And this explains why the original low-rank tensor decomposition doesn't work well, because the original low-rank tensor decomposition, you assume a really strong linear dependency that you may use the features even from the unrelated stations. So it's like this. But in the real case is that, okay, we have the weakly dependent on graph that you only relies on the local structures, which means that, okay, these stations, maybe you only use the features from its graph neighbors, and the rest is not considered. So we only use the features from the highly related stations. So you can see, okay, maybe we have this sparsity feature we want to achieve in this station dimension. So now this is our final formulation that, okay, based on the low rank decomposition, we first want to achieve the deep reason, the weakly dependency, that the U1 here is the U station, is basically the station mode, okay? So that instead of they are all correlated, they are all related, instead of that, we encourage this station, for example, is only correlated with the highly related stations, which means the graph neighbors, for example. So how to achieve that? We add L1 norm, which is to penalize the summation of the absolute value of each element of the U1. Then if we are minimizing the whole thing, then those unimportant elements will be penalized as 0. So this is the L1 normal, L1 regularization, and can achieve that. And also we have the graph, right? So graph is quite popularly formulated as a Laplacian penalty that can be written as this way, that if, for example, station I and J, if they are really close on the graph, which means the weight is really high, then the difference between the two related values, I and J, should be really small. The difference should be small, so that their value should be similar. So this is how we embed the graph information into the UI and UJ vectors. So overall, this is our final formulation of this task. And for the parameter estimation, so we basically use the block coordinate descent that we have the parameters lambda, U1, and U2 to UK and Y to be predicted. So we fix one, we fix 3, and to update 1 on each iteration. So for example, we update U1 and then we fix the rest. We can write the sub-problem and we can get a closed form. Similarly, for U1 that for U that is not U1, which means we don't have the weakly dependency and Laplacian penalty anymore, then it's quite an easy closed form. And for lambda, it's like this. And for Y, it's important. So for those observed set, we directly use the data X. And for the unobserved one, we use the CP decomposition result. Okay, so this is the parameter estimation. And how do we formulate the graph? So it's quite standard. For the geographical graph, if the stations if the distance between station I and J are more than k steps, for example, then they are 0, which means they are not connected. Otherwise, it's connected. And for the functional similarity, we collect how many hotels, shopping centers, schools, and residential areas. Then we get the POI vector, and we calculate the cosine similarity of stations I and J's POI vector. Then we get another graph. So this is how we define the two graphs. And this is the result. So the main part, first we look at the 5 badly performed stations. We can see that our method can have the improvements in those 5. And in other stations, we also see a lot of improvements as well. And also, as you can see, we add several regularizations inside. Specifically, we added the weakly dependence, and we also added 2 graphs. So how do we tune the parameter? So we basically use the grid search that we fix different low rank penalty and search for the best, the rest 3. So this is the best one we can find. Now another question is, so this is our design, weakly dependence and 2 graphs. So which contribution more, which contributes less? Okay, so we did an ablation study that, okay, based on the best optimal combination, we first delete all of our component design. Then you can see the MSE become really big, really bad now. And then we add the weakly dependence. You can see that the MSE drops 60%. And we add the contextual graph, it drops another 30%. And then we add the whether it's connected or not, the geographical graph, it drops another 10%. So at least in our data, in our setting, we observe that, okay, the weakly dependence is the most important and the contextual graph is the next. And this part, this other result I will skip. And this is the visualize that our method can also visually is quite close to the ground truth. Okay, so far, this is the whole prediction we discussed, and this is the most important part of the first lecture. And if you understand most of the contents, especially what is tensor decomposition, and how use tensor to do the prediction, and how the 2 graphs in fact the data behavior and the prediction. If you and get this 4 point and the 4 point well, then it's almost the most important part of the day. And another task, the second task I will look at is not prediction anymore. It is more like the individual analysis. So here I will slowly transition to the another topic. That, okay, previously when we look at the passenger flow pattern, okay, we say, okay, now there are 100 passengers here. We only look at the macro level 100, but we don't care about, okay, how different the 100 passengers behind the number. So that's why here we focus more on the individual level analysis. That, okay, maybe we can observe that some passengers, they prefer to travel from this type of origin stations at this type of time to this type of destination. and another passengers, they prefer differently. So basically, we can do some multi-clustering that we can cluster origin, destination, and time. This can help the metro operators to give some station-specific operation strategies. And also we can do the passenger clustering that we encourage some more customized policies or promotions, or maybe we can detect some anomalous travel behavior or travel passenger pattern. So, and also the two graphs, we want to keep in mind that is important in our previous result. So maybe it's also important in this result. So now the data we are looking at is not exactly a trajectory data, but more like the ODT data that, okay, the passenger one traveled from station 1 to station 3 at time 1 and arriving at, for example, time 4. So now I don't care about what's the arriving time, because usually every stop is 2 minutes. So we can basically just count the distance, and then we can calculate the travel time usually. So we only look at the 3 elements. ODT, T is the entering time. So okay, this is the passenger 1 travels this way. Passenger 2 travel differently. So imagine we have millions of passengers travel within a day. So how can we cluster all the information efficiently, right? So this I mentioned before. So this is our challenge, and the potential solution is actually quite interesting. We use the topic model from the NLP, from the traditional NLP way. Why? Because topic model, it can also handle millions of documents simultaneously. So it has really strong scalability, and also you can handle the sparse data. So this is just our first guess. Maybe it works, but how? So how can we use the topic model for the individual passenger data? So what is topic model? There's a really basic famous one back to 2010 called latent dirichlet allocation, this topic model. So for example, we look at the text. Okay, the topic model can tell you that, okay, these words are from one topic, and we name it, for example, is COVID related topic. And this blue, they are from another topic, green and yellow. So basically LDA can combine those words if they co-occur in different documents always together, then which means those words, they might be from the same topic. And maybe then we human interpret, okay, this topic maybe is about COVID or maybe about AI, so that we get that topic. So you see this word level, we will use the word level to do the ODT clustering. And okay, once we get all those color distribution for document 1, and for another document, document 2, if the 2 documents, they have the similar color distribution, then we can see that, okay, document 1 and document 2, document-wise, they are from the same cluster. Then in that case, we can cluster passenger also similar way. So here it sounds a little bit maybe still unclear, but you will see how we can do that later. So this is the basic word in the topic model. For example, this is, and this is the document. It's basically a bag of word. And this is the latent topic that connect the document and the word. And in our case, our word is the trip O and ODT. So that's why the word, the topic for the word is the ODT cluster I meant. And our passenger who has a lot of trips, can be seen as a document. So that's why here I meant, okay, the document level cluster, we can cluster passengers. And our topic, since we have ODT 3 dimensions, then we have the topic for ODT separately. So you can see the huge difference is that, okay, the original topic model is 1 dimension, and our topic model is 3 dimensions with ODT. So that's why we propose this model is called Tensor LDA model. And the graph, we will add up later. So this is the generative process of the LDA model. That what we really see is only in those words, but all those what's the potential topic, blah blah blah, they are all latent variables. So how do we generate to our to the word that we really see? So I will give some demonstrations. For example, if I tell you this topic, this passenger, this document is 50% about COVID and 25% about tech. So this is what we call a topic distribution theta for this document. And this theta for different documents, it will have different theta. So from this theta, we will do a multinomial distribution. We sample a topic from here. For example, we sampled the COVID topic. So z equals to 1. Let's do d equal to 3, AI topic. Okay, now d equals to 3, then we look at the third column of 5. For example, we get the topic word probabilistic distribution. And on the third column, we have the different word selections with different probabilities for this third topic. So from 5, we will do another multinomial distribution. We draw one sample, and then, for example, in the end, we draw real time. Then we get the word we really see. Yeah, the first one, real time. But of course, this probability, all those things need to be learned so that we maximize the posterior given the theta and the phi of the maximize the likelihood, sorry, of the topic of the document, right? So that's how we do the LDA model. So the big part for our Tensor LDA model is that we extend it into 3 dimensions for ODT separately. With each dimension, we have the topic JKL. So how can we understand this thing? So for example, our theta, our topic distribution for this Tensor LDA model, in this case now is a tensor with the dimension of J times K times L. For example, in the time dimension, it can be morning, afternoon, evening. In the OD dimension, it can be the residential, school, business, shopping area. So like this. So from this theta tensor, similarly, we draw a topic for this passenger. For example, for this word, for example, we get more school to business area in the morning. Okay, then we get the school topic for O. Then we refer to the school topic here, and then we do another multinomial distribution, random draw, and then we get this word for example, this passenger travel from HKU, and similarly for D, we travel to center. Similarly for the time topic, we draw from the morning topic and then get 9 a.m. So you can see it works like this way. And of course, the theta and the phi ODT has to be learned so that you match the real data to maximize the likelihood. And one thing, the last generative process is how to generate the theta and the phi, the distribution, the probability distribution of the multinomial. Then there's another distribution called Dirichlet distribution. which is specifically to work as the prior distribution of multinomial. Okay. So now we observe the two graphs of O dimension and D dimension. So how can we add the graph into the O and D? So this is how we add it. That okay, for example, if we look at only one graph on the origin dimension, that if two origin stations are close on the graph, which means this value is really high, then the probability that they are from the same distribution should be the same, which means they should from the same topic. So this is how we add it. So in the end, we also formulated as a Laplacian penalty. And since we have two graphs on O and also two graphs on D dimension, so you can see this regularization term is quite long. So overall, this is the loss function. We maximize the likelihood and minimize the Laplacian penalty. So that's why here is the minus. So this is the formulation model, the model formulation. And there's a really interesting part that, okay, this LDA model, how is related with tensor decomposition. So here's the conclusion that this LDA model, our tensor LDA model, is basically target decomposition we talk about. So how? For example, this is the probability of the trip ODT is in the dimension of ODT, right? The 3 dimensions. So this probability is decomposed as the probability of topic being in the topic JKL, which is a 3-dimensional core tensor JKL, and given the topic J in the O dimension, which is the mode matrix for O, and given the case topic in the D dimension, which is the destination mode matrix and the T dimension. So then you can see that, okay, it's basically we decompose this probability into the core tensor along each dimension, there's a mode matrix. So the LDA model is basically, the tensor LDA model is basically based on target decomposition. And here I will quickly introduce the algorithm because we don't really know what's the probability of a document, right? So this likelihood is intractable. So we cannot really estimate, but we can only approximate. So here we use the EM algorithm to learn the hidden parameters. And this is the experiment. We start from a small one that we only use 1,000 passengers for training. And we use the same graph we used. And here is the result we can see. And I will first focus on the O dimension, the origin dimension, which means the spatial dimension, the topic of that. So you can see that, okay, if this is the benchmark without the graph, and you can see our model can learn the topic and different functions quite distinguished to each other, which means it's good. So you can see that topic 4 is mostly capture the shopping area. Topic 5 is the major working area. 6 is the residential area. So compared to this benchmark, it's kind of is not distinguishable. This is the functional graph is working. And how about the location? Then we look at the 4 topics before that. Okay, for our topic 4, our model learned the topic quite concentrate, but the benchmark is quite scattered around. So which means that the geographical graph is also really penalizing the topic to be central, to be stay together. This is topic 5, 6, and 8. So overall, you can see the topic by introducing the Laplacian penalty is more compact. And this we already introduced the time dimension, and for the origin dimension, and for the time dimension, we can also learn some good patterns. For example, topic 1 and 0 and 1 is capture the 2 morning peak, and this topic 3 is capturing the evening peak, right? And also, the passenger cluster, we can also cluster it, that we use the JKL, the topic distribution JKL tensor. We calculate the Jason-Shannon divergence of each 2 passengers, and then we use the basic distance-based clustering method, so we can cluster some quite useful, interesting passenger clusters. For example, this one, we call it a student cluster because it travels from the residential area to school area in the first morning peak, and it travel from the school area back to the residential area in the midday around 3 p.m. So this we call it a student cluster. And we can also do some destination inference because we calculate all those probabilities. So we can calculate, okay, given O and T, what's the probability of going to the destination? So we can do some destination inference, and you can see that given O, this is the right D it should go. So our method make less mistakes than other method. So the last few minutes, I will quickly introduce another improvement of the LDA model, especially to cluster passengers. When we cluster the passengers, we calculate the distance between the theta 1 and theta 2, right, for these 2 passengers. So it's okay if we don't have too many passengers, but if we have millions of the passengers, the way how to calculate the pairwise distance, the complexity is n squared, which means it's quite complicated, especially if we have millions of passengers. So here we introduce another one-step way to cluster the passenger directly, and it's also the topic model. It's called short text model. That it has really simplified the LDA model. That okay, since our text is so short, that once we decide a topic for this document, for example, topic, then the whole rest of the topic and the whole rest of the text, all the words inside of this text, they have to share the same one topic. For example, COVID. Then all the words inside of the document only has only one topic to generate the words. So this is more simplified, so that we also extend it into a 3-way. So I will skip the technical detail, but I will show a demonstration. For example, we have the only theta, the vector here. Maybe the student, maybe the passenger clusters can be an intern or student or white collar. Then, for example, we get the intern topic for this student, for this passenger. And then from this topic, we will be using it for ODT strictly. So for O is also from the intern topic to get, for example, HKU. For D is also the intern topic. For T is also the intern topic. So you can see that we don't have the topic of JKL anymore, but we just have one unified document-wide, the short topic. And the really interesting thing is that, okay, the LDA is actually based on Tensor decomposition we mentioned, right? So this short text model is actually based on the CP decomposition. So how? So basically, the probability of the document is the probability of the different, the short, big topic, and the times given this topic was the topic for each word. And for each word is basically O times D times D because they are IID. So then this is P, so this probability of the topic is basically vector theta. And the rest is basically the mode matrix along each dimension. So you can see the difference that, okay, LDL model, we have the dimension of JKL, the core tensor inside is the tensor topic, is the tensor decomposition. And here, short text model is the vector inside. And it only has one rank to decide, is the C. So it's the CP decomposition. So yeah, this is the interesting part. And we use the give sampling to learn the topic, and I will skip this part. And this is the topic we learned, that we start from super high big value, and then you will decrease over the iteration, and you can see it kind of converged around 25 clusters for the passenger. And this is the visualization of the passenger clusters we learned. And you can see that our model puts the same passenger clusters more tightly, which means it's good compared to the rest. So overall, we show that, okay, how the high dimensional data, specifically the spatial temporal high dimensional data, is popular, how it's popular in the smart transportation area, and also maybe in the smart market or smart energy or smart manufacturing. We all can observe this spatial temporal high dimensional data, and we show that how tensor can help this way to solve it. And also in the individual level, we also show that how the tensor topic model can learn some interesting clusters for personal recommendation or for more customized services. And there are also some new things happening in this tensor area, a new type of decomposition called tensor train decomposition, which is better, and people claim that because it has really good numerical result, and people also combine them with the neural network to speed up the training because it can compress the data, the tensor parameter to be learned by the tensor train decomposition. And also people combine them with the time series model to do a longer term prediction, can, for example, up to 20 days. And also, maybe there are some new problems. For example, we only look at inflow pattern. And we can also look at, for example, not only inflow, but also outflow at the same time. So this is the flow entering the station 11 and getting out from the station 1. So if we sum up the whole row, then we get the inflow data of that we used in the first part. So this OD flow is actually expanding the 100 stations into a 10,000 OD pairs. So of course the data will become way more sparse than in that case where our decomposition still work. And how this graph will affect the OD data will be in the same way of the inflow data. So this is the open question. And also the metro station map we look at was 2017. And now after 5 years, things already changed. And there's already a new line built up. So due to the urbanization and the expanding network, so for the new stations, before we set it up, can we already kind of predict how much the passenger value will be in these new stations, and also where the new stations will affect back to the old stations. That's also quite interesting. And the last, that okay, there are some data is also has really 7-year long data, and this new area called continual learning, can we find out some long-term evolution pattern of the traffic flow, and also are they long-term patterns or are they just occasional phenomenon? Can we decompose different patterns? So overall, there are a lot of different potential new problems in this area, and as it's like a hiking in the mountains, that there's always new mountains to be hiked, and there's always higher mountain